Hello students, so welcome to third lecture of polymers. So in last lecture we discussed about condensation polymerization and some important condensation polymers. In this lecture we will discuss about co-polymerization reaction and natural rubber. So as the name suggests, in copolymerization we will use more than one type of monomers. When more than one type of monomers reacts with each other and if they are allowed to polymerize, then it is called copolymerization reaction, and the product obtained this way is also known as copolymers. So copolymers can be made not only by chain growth but also from step growth polymerization, and it contains multiple unit of both type of monomers used in this polymeric chain. So as for example, here one example is mentioned. When 1,3-butadiene and styrene reacts with each other, it gives us butadiene styrene compound. It is also known as BuNa-S. In this compound, when reaction occurs, actually bond transformation takes place. That means, as we can see here, we have double bonds, and these double bonds will shift here. That means when we have a structure like this, okay, so this bond will break. That's why this carbon needs to form one bond, and this carbon also needs to form one bond. This bond breaks, so now this carbon wants to form one bond, and this carbon also wants to form one bond, and these two present at the center will form bond with each other. So now double bond is shifted from 1 2 and 3 4 to 2 3. Okay, so that means in buta 1,3-diene, initially double bond was between first and second carbon and third and fourth carbon. After rearrangement, it will shift between second and third carbon. Similar situation occurs here. Here we have phenyl ring, then we have two carbons attached with each other using double bond. So this bond will break. That's why both of this carbon needs to form bond. So these two carbon will form bond with butadiene molecule, and eventually you will get this compound, and it is known as BuNa-S. Okay, it is also called BuNa-S. Now this type of polymers, copolymers, have comparatively quite different properties from homopolymers. So here given example is a good substitute for natural rubber, and it is used for manufacturing of automobile tires, floor tiles, footwears, etc. Now let us move on. Next point, rubber. In rubber mainly we have two different types, natural rubber and synthetic rubber. So first of all, let us discuss about natural rubber. So rubber is a natural polymer and it possesses elastic properties. That's why it is known as rubber. So it is termed as elastomeric polymer. Now generally, because of multiple atoms present in this type of molecules, because they are comparatively large molecule, multiple intermolecular attractive forces will be possible in them, and that's why they have stretchability or flexibility. That means it possesses elastic properties, and because of a large size of molecule and multiple intermolecular or weak binding forces, they will be coiled like this. That means if we have straight chain of polymer, because of intermolecular attraction, it will coiled up like this. So it possesses coiled structures, and to increase the strength or to gain its initial position after releasing the force, we will add some bonds. By adding certain chemicals, we can create some cross linkings between them, so which increase the stretchability or elasticity of this type of rubber. Now rubber has many different type of uses, and it is obtained from rubber latex, which is the colloidal dispersion of rubber in water. Now actually rubber is a one type of liquid substance. When occurred from the nature, it is occurred from the rubber trees, and these type of trees are found in India, Sri Lanka, Indonesia, Malaysia and South American regions. Now when we observe rubber at the microscopic level, then it is we can say that polymer of isoprene, that means 2-methyl-1,3-butadiene, as we can see here. So we have isoprene molecule here, and same type of rearrangement as we discussed in Buna S, same type of rearrangement of bonds will takes place here. That means these double bonds will shift between these two carbon. That means initially double bonds are between 1 and 2 and 3 and 4th carbon. After reaction it will be something like this. So now double bond is shifted between 2nd and 3rd carbon like this. So that's why 4th and 1st carbon needs to form bond, and they will end up forming bond with adjacent molecule, and multiple same type of monomer will combine with each other and you will get rubber, which we can see here. Okay, so here we have natural rubber. If we want to give numbers, then this will be numbering of single isoprene molecule. Now this isoprene molecule is also called as cis-1 for polyisoprene. So why it is called cis-1 for polyisoprene? So if we observe structure of natural rubber, then let us observe connection between two different monomers. So this will be our first monomer, and from this point this will be our second monomer. So linking, first of all let us give numbers 1, 2, 3 and 4, these 4 numbers for first monomer, and 1, 2, 3 and 4 number for second monomer. So bond is between 4th and 1st. Okay, so same type of repetition will be observed throughout the molecule. Always first carbon and 4th carbon are in attachment with adjacent monomeric molecules. Now if we observe the position of this first and 4th group, then because of double bond, if they are on same side, then structure will be called cis, and if they are on opposite side, then it will be called trans. Okay, so as we can see, if first is at the bottom side, then 4th one is also present at bottom side. That's why they are on same side, and that's why we are calling it cis molecule. Okay, so that's why it is called cis-1 for isoprene. Same type of repetition will be observed. These two carbons are attached with adjacent molecule and they are on same side of double bond. That's why it is called cis isoprene. Now isoprene molecule consists of various chain held together by weak van der Waals attraction. That means if you observe this molecule, then because of sp3 hybridization of carbons, it will be zigzag in shape, and two adjacent carbon will try to attract each other. If they are comparatively close enough, then attraction will occur. So if this is the structure of rubber, then if carbon is present here, here, here and here, then they will produce weak attraction with each other, something like this. And because of this type of attraction, they will shift comparatively closer to each other like this. Okay, so if attraction proceeds, then it will shrink and it will behave as spring, and as the number of this type of attraction increases, more and more coiled structure will be obtained, and because of coiled structure, it possesses elastic properties and we can stretch it like springs. Now vulcanization of rubber. So what is vulcanization process? If we want to use this type of rubbers practically, then we need to increase their strength. Natural rubbers are comparatively very weak in nature, and they are not resistant against the attack of oxidizing agent. That means if we place them in open atmosphere, eventually it will oxidize itself and it will start decomposing itself, and it will lose its original properties. And at the higher temperature it becomes soft, and at lower temperature it becomes brittle, and it is water absorbing compound. Now, to improve its physical properties, we need to add some chemicals into it which increases its strength. It is called vulcanizing process. Now, because of vulcanizing, cross linking will occur between rubber chains, and as the cross linking increases, it will decrease the flexibility or elasticity, but it will add some strength. That means as the rubber becomes more and more vulcanized, it loses its elasticity and it increases its strength. As for example, natural rubber, we can compare it with tires. So tires are comparatively vulcanized rubber, so it is comparatively less flexible but comparatively more strength. It has more strength. If you compare piece of tire with elastic rubber band or eraser, then we can easily see the difference. Erasers are comparatively soft and flexible. On the other hand, tires, they are comparatively hard and less flexible or brittle. So let us observe the reaction of vulcanizing. So at the higher temperature between 373 to 415, sulfur is added with rubber, and it increases cross linking between the two different chains or two different adjacent locations in the same rubber chain. Normally it occurs between double bond, site of double bond, but it is not always necessary. So we can see the different type of possible structures of linking with sulfur. So normally if we temporarily ignores the sulfur, then double bond will be present here and here. So if we vulcanize the rubber, then these double bonds will break, and this carbon will form bond with sulfurs, and you will see something like this, structure like this. It is the location of double bond, at the site of double bond. But in certain cases, as we can see here, if we ignore the sulfur from here, then it will be something like this. We have chains of the rubber, natural rubber, like this. Now one hydrogen will be removed from this side, and one will be removed from this side. Now this both carbon needs to form bond, and that's why sulfur will form bond with them, and we will get this type of vulcanization. Okay, so this is vulcanization process, and with the help of this type of vulcanization we can increase the strength and the resistivity towards the oxidation of rubber. So in the manufacturing of tire, 5% of sulfur is used as a cross linking agent.